Yeah, hello, I'm Chris Rakakis from MIT, and what I'm going to be talking about today is stability optimized high order methods for stiffness detection for pathwise stiffness and stochastic differential equations. Or the shortened title is how you can use HPC to derive better HPC algorithms, right? And that's really how it ties into HPEC. So, what is the problem that we're looking at, right? Because that's a pretty giant title, so I want to kind of give a quick overview of why we're interested in this topic. And really, our interest becomes because chemical reactions are noisy, right? So if you take anything that's going on in biology, you have this randomness for how all of your chemicals are flowing around. And so the randomness in the chemical concentration levels actually is what guides a lot of developmental processes. So there's a lot of things that happen in biology, like the segmentation between different parts of the brain, which happen because of the natural fluctuations that occur, right? So if you get rid of the randomness or you get rid of the stochasticity, you actually will cause the system to do the wrong thing. So this randomness is really crucial to how a lot of biological processes work, and it's also crucial to how a lot of bad biological processes work. So many cancers can be attributed to a random process gone awry, right? There's a probability of it ending up in a wrong cell state, and these transitions will happen every once in a while, and then your body has to either fight it down, or if it doesn't, then that's when you start to have something malignant start to happen, right? And another thing is that proper treatment and dosing for different diseases requires understanding the pharmacology in a stochastic sense, because everyone's reaction is going to be different, and you want to make a dose be safe with respect to the noise within the body and the noise within the metabolism. Now, this is a very interesting problem because SDEs and stochastic processes are not ODEs, right? So here's a very specific property, this pathwise stiffness, that is not seen in a deterministic system. And so here is an example of one of these SDE systems where we have steady states at 0, 1, and 2. And here is a solution of that system that's described a bit more detail in the paper. And essentially what we see here is that you have switching between different steady states, right? And the reason is because if you're randomly jostling around one steady state, you can get far enough away from it that you can then jump to the other one. And this is what we call pathwise stiffness, right? So this model is essentially non-stiff. But every once in a while, you have these gigantic flips from one side to the other, and that introduces some kind of numerical issues, right? And you don't want to dampen them. You don't want to get rid of them because these switches are really the thing that we want to understand in the system. And so here is like this interesting case where if you're to look at it as an ODE, you have no stiffness. And so it really is a purely stochastic phenomena that we have to handle correctly. So how do you solve a stochastic differential equation? So most people know RungeKutta 4, right? That's the ODE solver. And if you were to look at what RungeKutta 4 is like, or what the Euler method is like, it's really just you do a bunch of function calls on previously computed state values, right? You use K1 to calculate K2, you use K2 to calculate K3. You use a bunch of different function calls, and then you do a linear combination to be able to get what your next state value is, right? And that's essentially what you do for stochastic differential equations as well. So you take this general form here where you say this is the essence of a RungeKutta method, right? I have these states where I'm doing linear combinations of previous states to be able to calculate what I should do a function call at next, and then that gives me all my different k's, and then I do a linear combination of k's, and that gives me our future. So this is how all of these, fifth order, ninth order RungeKutta methods for ODEs are generated. When you go to stochastic differential equations, you can prove that here, for example, is a given stochastic RungeKutta method where there are certain ways that you have to define these random numbers, but other than these definition of random numbers, it is the same thing where you have coefficients in here, you calculate values of f, you calculate values of g, your diffusion function with the stochastic differential equation, you add up a bunch of values, you take linear combinations of them, and that's going to give you your future step, right? So it's the same kind of process. How you're calculating f at a bunch of points, you're calculating g at a bunch of points, you step forward, and then you repeat this process, right? Now it's a bit more difficult because you can see that there's more steps to this RungeKutta method, but it's still in general the same kind of idea. It's just you have, instead of just having one small table of coefficients, now you have coefficients that go here, you have coefficients that go here, you have coefficients that go here. So you have this gigantic table of different coefficients, right? And so then the question of, what is a good stochastic RungeKutta method for solving these kinds of equations is really just defining, well, what are the good coefficients for this table that give me the properties that I want out of my stochastic RungeKutta method. And so, for example, the one thing that's been shown before is that you have a bunch of these order conditions. So if you satisfy, for example, that the vector of alphas times a vector of ones is equal to 1, then you will, that's one of the things that has to be satisfied to have a order 1/2 method. So strong convergence of stochastic Runge-Kutta methods is a lot lower than ODE methods because you don't even have that this solution is differentiable. You have to come up with a new calculus in order to define this, and within this calculus you have orders growing by 1/2, and you have all these different conditions that are kind of growing that you need to satisfy in order to have a method that will be higher order, which means you get less error for the same time step. Now, the one thing they might want to think here, though, is you say, okay, I have a form for my RungeKutta method. I have order conditions I have to satisfy. So let me just, if I need to deal with stiffness, then let me just define an implicit version. An implicit version might be able to handle this stiff stochastic differential equation. But the difficulty is that the stability of numerical integration of SDEs does not necessarily follow the rules of ODEs, right? And there's this really nice paper on this, the effectiveness of implicit methods for stiff stochastic differential equations, which essentially describes how, in stochastic equations, you have this randomness about how everything is jostling around. And the way that ODE methods really get really large time steps, right? These L-stable integrators that people use, like CVOD, BDF, they're dampening these high order frequencies. And if you try to do that in a stochastic differential equation, you actually will compute the wrong solution. And you'll see this, I mean, in the case of this pathwise stiffness that I was talking about, right? If you dampen out all of the high frequencies, then you actually won't have switching between the states because it's those higher order frequencies that is causing that jumping between the states. And so you'll completely change from having two steady states that you're changing between to one if you try to use an L-stable integrator on here. So, the ideas of stability and such just don't necessarily apply. You have extra errors introduced, or if you do try to fix that up, then you have to have a lot more difficult things that you have to calculate to get around that. So there's a lot of things that kind of show that implicit integrators are not necessarily as useful in the stochastic differential equation case as they are in the ODE case. So is there anything that we can do, right? Like if we have a very stiff equation, is there anything that we can do to make better integrators for this case? Well, what we can do is we can, just like in the ODE case, we can define an idea of stability for a stochastic Runge-Kutta method by using the linear stochastic differential equation. So we take a linear stochastic differential equation and we ask for what step sizes does it does for what step sizes does the method converge to 0 instead of blowing up to infinity, right? That's the same. This is the same idea as how you define stability in the ODE case, except now we're talking about the stability of the mean in the case of the linear stochastic differential equation instead of the linear ordinary differential equation. Right, so this is a very similar definition. If you want more on this definition, you can check out Cloden's book, or you could read the paper a bit more. Essentially, what we do here though is we take one of these definitions of stiffness and say what we want is we want just a explicit Runge-Kutta method that is really high order and extremely stable, the most stable we can get. And so under this definition of stability, we get this equation where every single kind of term in here, those are all matrices and vectors, right? And we have to take inverse of these. And so if you actually want to write out in terms of the coefficients, what equations you get a few million lines of code. In order to actually calculate that, we had to put that into Mathematica and run it on one of the HPCs for a while, and then get millions of lines of code for what the order conditions are in terms of the coefficients. So that's intractable to handle by hand, right? So it becomes an HPC problem to figure out what is the optimal solution for choosing this RungeKutta method to then do HPC calculations with, right? And so what we did was we said, okay, the stability region is defined by where some stability function is less than or equal to 1. So we can calculate the area of the stability region by doing the double integral over the space of that we're trying to calculate the stability for. And what we want to do is we want to maximize this area calculation for the stability region subject to the order constraints, right? So that would give us the order 1.5 algorithm that would the strong order 1.5 algorithm that has the largest stability region. And so then what we did was we used the common HPC along with the genetic algorithm from NLOpt, and we built CPU.
Christopher,
Yep.
we've got 1 minute left.
Yep, and we built some CPU kernels or GPU kernels to be able to parallelize this calculation well. And we got a new method which was taking, it has a stability region about 5 times, which means it can take about 5 times as large time steps. And so then what we did was we took this method and we tried it on a bunch of these different problems, and we saw that we got about for short stochastic differential equations, we got about a 6x speedup versus the previous adaptive method that we came up with, almost 2 orders of magnitude against the common fixed time step methods. When you get to very harder, longer stochastic differential equations, you cannot even plot the time for the fixed time step method anymore because they won't run in the year that we're able to run them. And here, even against the adaptive methods, we've increased the stability region by 5 times. We got about a 6 times speed up. So it very closely matches the theory. And so all this is implemented in the SciML open source software ecosystem, which has things like automated physics-informed machine learning, which can incorporate stochasticity and automatically learn what the missing equations are of some physical system. And if you want to know more about this whole ecosystem and these types of methods, I am running a course on HPC mixed with machine learning. It's the MIT 18337 course, Parallel Computing and Scientific Machine Learning, and you can check out this link for more information. So thank you very much.